So in this video we are going to focus on the wave function or the orbital for hydrogen atom under physical chemistry. So when you solve the Schrödinger equation, you will get the information about the wave function or the orbital, and what comes out of it is the three quantum numbers, and those quantum numbers are necessary when describing or necessary to describe the orbital or the wave function. So let's talk about those quantum numbers. The first one is let me yeah so the first one is the principal quantum number denoted by letter n. The second one is the angular momentum denoted by letter L, and the third one is the magnetic quantum numbers. So this one, let me have my highlighter so that I will be so this one, the principal quantum numbers denoted by letter N, it focuses on the energy level or describing the energy level, whether it's energy level number 1, 2, 3, 4, 5, etc, etc. And this one, the angular momentum quantum number, it focuses now on the subshell or the shape of the orbital, whether it's S, P, D, F, and so on like that. And lastly, this magnetic quantum number denoted by M or M subscript L, this one now focus on the specific orbital, the orbital orientation, whether it's px, py, pz, and so on like that. So now the relationship between these three is as follow, or rather let me start by introducing this one. N, you can see n is start from 1, 2, 3 all the way to infinity, and then let me describe the angular momentum with respect to principal quantum number, or the relationship between the two is that L start from 0, 1, 2, 3 all the way up to n minus 1. So all the way up to n minus 1, this same n here, which is the principal quantum number. And lastly, the magnetic quantum number, it start from negative L down to 0 and all the way up to positive L, like this. So now let's try to describe an orbital, using of course all these three quantum number that I have just talked about, right, which is n, L, and m, whereby this n is the same n that I was talking about, which is the principal quantum number, and this L is the angular momentum quantum number, and lastly this M, we can say M or M with subscript L here, is the magnetic quantum number. So the wave function will be given by this one. So in other words, it depends on the r, theta, and flux here. So it depends on the radius and all this angle, right? So that's the wave function. So now the wave function for a ground state now will be this one here, with 1, 0, 0. In other words, this this one here, it's n, which is the principal quantum number, and then this L here, it's 0, which is the angular momentum quantum number, and this last 0 here, it's M, which is the magnetic quantum number. So that's for ground state. So We have the next one. So in other words, this one, this wave function is called the 1s orbital. Let me show you how did we come about. Firstly, we know that n designate the shell or the energy level, which is 1, 2, 3, and so on and so on like that. And L is the subshell, which is responsible in describing the shape of the orbital, whether it's S, P, D, and so on like that. So lastly, the M, uh, it describes the orbital orientation or the specific orbital, whether it's px, py, and pz like that. So for L, if L is equal to 0, we know that this L, which is the angular momentum. So if it is equal to 0, it simply means that, or describe the s orbital. And then when L is equal to 1, it's now p orbital. And when L is equal to 2, we're talking about the d orbital, and so on and so on like that. Like here on, when L is equal to 3, it's f orbital, and so on and so on like that. So now take note of this. For L is equals to 1, in other words, that's the p orbital. The value of m, or m, ranges, from it's -1, 0, or the possible value of the magnetic quantum number, or ml, are these three one here, which are -1, 0, and also 1. In other words, when m is equal to 0, it simply means that that's the pz or pz orbital. And when m is plus or minus 1, that's the py or px orbital. So in short, to understand these things, when n equals to 1, this n here, when it is equals to 1, it simply means this one here. It simply means that there is only one subshell. In other words, that one subshell is the one with L equals to 0. And when n is equal to 2, it simply means that there are two subshell. And then the 2s subshell, the one will be with L equals to 0, and the other one will be the 2p subshell with L equals to 1. This L here, which is being equals to 1, and so on like that. So now let's focus. Let me draw the table here and explicitly show you this wave function here, and how do we write these n, l, m values without confusion. So look, if we have n equals to 1 and L equals to 0 and ML is equal to 0, so the state label will be like this. In other words, this first one here, or this one here, is occupied the position of n. You can see the second one here, it occupied the position of L, and lastly this 0 here, it occupies the position of ML, which is the magnetic quantum number, and the wave function will be like this. Right? So look at the wave function. If you check the wave function, normally it's written as its wave function, and we write LMN, but in position of this LMN, we substitute these values here, which are LMN. In other words, this one here is for L, is for N, NLM. In other words, the red one is for N, which is the principal quantum number. This one here is this one here. And then this 0, it's this one here, is the angular momentum quantum number, denoted by letter L. And the ML is this one here, which is the magnetic quantum number. So it's like this. And then this one is the 1s orbital. So same applies here. If we replace that, now this time around we are talking about 2 now, not 1, and then you will still realize that in terms of the state label, it will be 200, and then the the wave function will be 2 0 0. In other words, this is not 1, this one here, it's 2, or it's supposed to be 2, this one here. Let me write it well. This one is 2, yeah, like that, 2 0 0, like that. And then it's going to be 2s here, because we are talking about 2s here. So now let's talk about the physical interpretation of the wave function. In other words, here now we are going to understand the significance of this wave function. Right, we are going to talk about the significance of this wave function. Why do we care so much about the wave function? In other words, we are not just interested in finding how tight the electrons are binding or bind to the nucleus, but we want to find out how those electrons exist, around the nucleus, like that. So that's why we do care about this one. So in other words, the wave function do get to the probability density, or the probability of finding, the so the probability density, it's more like the likelihood, that you will find the electron at a certain location, uh, you know. So that's the likelihood that the electron will be found at a certain location here, right? So that's the probability per unit volume. So you can see here we do have the phi, or the flux here, and then we have the theta, and we have the radius r. We have the z-axis or the z-axis, we have the x-axis, and also the y-axis. So yeah, let me write next here. And then now let's talk about the shapes and the size of the sp orbital. So to consider this 3D shape of the orbital, we can write the wave function as a product of radial wave function and also the angular wave function, like this one. So you can see here that this is the uh, radial wave function, which is this one here, and this one will be the uh, angular wave function. So we can explicitly write them as like this, and then this will be equals to the radial one multiplied by the angular wave function, whereby this one is the radial wave function and this one is the angular wave function. So let me show you a table here. Don't worry about this table. I mean, you don't need to memorize this table. Normally it will be provided for you, this table. Yeah, so you can see here that we do have the wave function, the radial wave function on this side here, and on the right hand side here we have the angular wave function. So for a ground state one, let's say if we have n being equals to 1, we are going to have something like this, or the uh, radial wave function will be like this, and then that's when 0 l is equal to 0 and ml is equal to 0, we are going to have the angular wave function like this one here. So a is the Bohr radius. In other words, this is the constant, and its value is equals to 2.9 picometer. That's the a0. This a0 here, it's a constant. So now let's consider ground state or 1s hydrogen atom. In other words, we're going to have wave function 1 0 0, and then it's going to be like this, and then we're going to multiply by 1 over 4 pi to the power half. So in other words, this is, you can see here that we get this expression here down here from this one here. So let me also have my pointer ready so that I can show you where they come about of this. So look, This is the wave function, right? NLM. So n, we wrote 1 here. So instead of n, this n here, we're going to write 1. So that's why I wrote 1 here. And then in terms of L and M, it's 0. You can see L here, it's 0. And M here, it's 0. So that's why I wrote 0, 0, right? And then from there, the radial wave function is this one. And the radial wave function is given from this table, is this one here. We just copied it as it is and then multiply by this one. Now the angular wave function is this one here, 1 over 4 pi to the power half. So that's the one that I wrote here. But now for a ground state or the hydrogen atom, the z or this z is equals to 1 for hydrogen atom. In other words, I can substitute 1 here and simplify. So after substituting 1 or replacing z with 1 and simplify, I got the answer being equals to this one. So this tell us something. This tell us something that you can see here that the this value here, or this expression here, it is simplified, but it does not consider the theta and also the flux or the fly. So why it doesn't consider this angle? So this simply means that all the s orbital now, you know, the either it's 1s, 2s, 3s, and so on and so on like that. So all those s orbital, they are spherically symmetrical. They are spherically symmetrical. In other words, they are independent of these angles here. They are independent of these angles. So that is it. Thank you for watching the video. Don't forget to subscribe to this channel.